Water systems in the desert are a contradiction. They are designed to deliver something reliably that the environment cannot provide on its own.
In arid regions, water flows through cities with the expectation that it will always be there, despite limited rainfall, shrinking reservoirs, and growing demand.
That reliability is not natural. It is engineered.
For decades, one assumption shaped how those systems were designed. Drinking water must come from a small set of clean, natural sources, while wastewater must be kept separate and disposed of. This separation made sense historically, because keeping wastewater away from drinking water supplies dramatically reduced disease and protected public health. However, that model only works when fresh water is abundant. In much of the western United States, freshwater supplies are increasingly limited. Population growth, prolonged drought, and climate variability all place pressure on the same small pool of usable water. At the same time, enormous volumes of wastewater are produced every day, water that has already been collected, treated, and managed.
Yet, under that traditional framework, water is treated as waste rather than as a resource.
And this creates a central problem. How do you safely expand water supplies when natural freshwater is no longer sufficient?
The solution is not to rely solely on freshwater sources, but to diversify our water portfolios to include wastewater, something that would have been unimaginable not long ago.
Modern potable water reuse systems treat water using several independent purification steps, each designed to remove different classes of contaminants. This is now standard practice in large-scale water reuse facilities and is required to meet public health protection goals.
One of the most critical barriers in this process is reverse osmosis. Reverse osmosis uses a semi-permeable polymer membrane and high pressure to separate water from dissolved contaminants. Water molecules pass through the membrane, while salts, chemicals, viruses, and pharmaceuticals are rejected and removed. This separation occurs at the molecular scale. Reverse osmosis is not simply filtering particles, it is selectively allowing water to move through the membrane while holding nearly everything else back. Because of this, reverse osmosis consistently achieves extremely high removal of contaminants and forms the backbone of advanced water purification systems. However, even reverse osmosis is not used alone. Potable reuse regulations are based on required pathogen log reduction targets, which define how much viruses and other microorganisms must be removed to protect public health. No single treatment technology can meet all of these targets by itself. That is why modern systems rely on redundancy, multiple barriers working together rather than a single point of failure. After reverse osmosis, water is exposed to high-intensity ultraviolet light combined with hydrogen peroxide. This advanced oxidation process disinfects the water and destroys trace organic compounds that may remain at extremely low concentrations.
When viewed this way, water is no longer defined by where it started, but by how thoroughly it has been treated.
In water-limited regions, potable reuse is not an experimental idea. It is a carefully regulated multi-barrier system built on membranes, physics, and chemistry, designed to turn scarcity into reliability.